Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 35 of our DC of our machines chapter, in which we will be studying about characteristics of DC motor and we will do questions on this topic. So let's first start with the characteristics. What are the different plots that we are interested in? We are mainly interested in these three plots. So in case of generator, we were mainly interested in voltage and currents, because in the output we are getting some electrical, right? Electrical output. That's why we were mainly interested in voltages and currents. In case of motors, the output is mechanical. So in case of motors, the output is mechanical. So as the output is mechanical, so we will be interested in mechanical parameters such as the speed. So speed, either you can write it in RPM or sometimes they write in omega, that is known as the radian per second, right? Both of them say the almost the same thing only. Okay. Also the torque is also a mechanical parameter. With respect to load means the load current IA, whatever current I am supplying, that's it. So these are the mainly three parameters around which our characteristics of DC motor will depend on. First one is the speed versus armature current. So how does my speed change with respect to change in the armature current? If I vary my armature current, how will the speed change, right? That is what we want to know. So this also sometimes is written omega versus IA. Then the next one is the torque versus armature current. How does the torque change with change in armature current? Okay, so this is TIA only because there is no omega equivalent here. And the third one, the most important one, this is similar to the external characteristics. Okay, similar to external characteristics in case of generators. External characteristics in case of generators. Okay, so basically torque armature current. So speed torque is speed versus torque, or we can write omega versus torque. This is the most important one for motors. Okay, in case of motors, most important one. So this, right, we will analyze this comprehensively. Okay, of course all three we will analyze anyways. So we will visualize how the speed changes if I change my torque. Okay, if the load torque changes, then the how the speed will vary. Okay, so let's start off with DC shunt motor. In case of DC shunt motor, very basic thing I know. So we will start off with DC shunt motor. So in case of DC shunt motor, I know what is the like key wheel, key seal, all those things. So my EB, right? EB will be equals to Vs minus Ia Ra. And one more thing I know, what is the EB equals to? EB is equals to, EB is proportional to flux and speed n, right? Because it is 5 ZMP upon 60A, all the other are almost constant. So EB is proportional to flux and speed. So I can write EB is equals to some K prime Km motor constant into flux into speed. Okay, and again if I assume that the flux is also constant, if I assume the flux is also constant, then it will be same, because here, right, the terminal voltage is constant, right? So what is the field current? It is Vs upon Rsh, right? And in case of motor, the great thing is we make our terminal voltage to be constant, right? It is DC motor, so terminal voltage will be constant. If terminal voltage is constant, hence my IF is also constant. If IF is also constant, hence my flux is also constant. Flux does not vary. So basically ultimately, right, EB depends on speed only. EB depends on speed only. So ultimately what I can say, this equation will be Km phi n equals to Vs. Vs is just a constant value, Ia IA is the load current, RA. So from here, right, speed will be equals to 1 by Km into phi, which is just a constant number, into Vs minus IA into RA. Okay, so the first equation is already done, right? So my speed is just a straight line with negative slope. So the speed current characteristics will be a straight line with a negative slope. Very simple to understand. But here, right, very simple thing we have not discussed, the armature reaction, right? So the speed current characteristics this is the current, this is the speed. Okay, so this is the speed, this is the current. So what I can roughly say, or it is proportional to omega only, because like omega is what? Omega is 2 pi n by 3, omega is 2 pi n by 60, so both are the same only. So the speed load current characteristics will be somewhat like this, right? It will be like, it will reduce slightly. Okay, now it will be not completely linear in this region. Why it will not be linear? Because as the load current increases, what will happen? If the load current increases, the armature reaction will increase, right? So this speed is known as the, this speed is known as the no load speed. NO is known as the no load speed. Now if the load current increases, what will happen? If IA increases, we have not discussed about armature reaction. So armature reaction increases. Okay, if armature reaction increases, what happens? The flux actually reduces. So the speed actually will increase. Why? What was the equation of the speed? Equation of the speed was this, right? If you see, flux was inversely proportional, sorry, speed was inversely proportional to speed. Sorry, speed was inversely proportional to flux. So if flux reduces, speed will increase. So speed actually will increase, right? So this graph is with armature reaction neglected. Now if I consider the armature reaction, the graph will be somewhat like this. That also will be reducing only, right? That graph also will be reducing only, but it will reduce slightly in lower values. It will not reduce like linearly, it will reduce like this. It will reduce non-linearly because armature reaction itself is a non-linear phenomena. Okay, so roughly it will be like this. Okay, so this will be the speed with armature reaction considered. Okay, so this graph is with armature reaction considered. Now what is the next one? Next one is the torque load graph, right? So torque load graph. So speed already we have discussed. Now let's discuss about the torque and load. So torque load, I know what is my torque proportional to, right? Torque is proportional to, if you remember, torque is proportional to phi and Ia, right? So again it is some constant K T phi Ia, right? So if I assume my flux to be constant, if flux is assumed to be constant, that is armature reaction is neglected, then torque is directly proportional to Ia. It is just a linear line. So if I have no load, then the torque also will be 0. No load current, torque also will be 0. So it will be just like a straight line. Okay, so this is with armature reaction neglected. Now if I consider armature reaction, then if my Ia increases, the flux will reduce. So what will happen to torque? So for lighter loads, at lighter loads, right, torque will not change much because Ia is small, so reduction is phi also will be smaller. So for lighter loads, the change in flux as like for lighter load, armature reaction will be negligible. So the change in flux also is zero, almost zero, no change in flux. So if change in flux is zero, so roughly for lighter loads this will follow the same linear graph. Okay, now when the armature current becomes very high, when Ia is very high, then of course flux also will reduce drastically, so the reduction will be very drastic. So what will happen? Previously my torque was equals to k into phi kt into phi Ia. Okay, now let's assume few numbers here, right? So if I assume Ia to be 1 ampere and my flux to be 1 Weber, right? So torque previously was equals to Kt. Now for the same case, if I consider armature reaction, so if for the same armature current 1 ampere, the flux might be a bit less, that is 0.9 Weber. So the torque will be Kt into 1 into 0.9. So this will be 0.9 Kt. Okay, so 0.9 Kt. So instead of it being following this line, it will be somewhat lower than this. So if armature reaction is considered, the actual graph will be somewhat lower than this. So here the armature reaction is considered. Okay, so yeah, this was the basic graph. So combining these two graphs, I will try to make the speed torque graph, right? Speed torque characteristics. So how do I draw the speed torque characteristics? How will I draw the speed torque characteristics? I need a relationship between the speed and the torque. Okay, I need a relationship between the speed and the torque. Okay, so this will be the speed torque. So what things I know till now? I know the speed equation. Speed equation is this. I know the speed equation. I know the torque equation, this. Can I combine these two? So I can replace here Ia with torque, right? I can do that. I can replace Ia with torque, right? So my speed, so my Ia is what from the second equation? Ia is torque divided by Kt into phi. So speed is equals to 1 by Km into phi into Vs divided by T into phi into Ia. So T, so directly I can write that what is torque equals to, torque is basically equals to, it is just a, it will be almost so if I increase my torque, what will happen? If I increase my torque, it should also be something linear. So yeah, it should, if I don't consider armature reaction. So what is my torque? Torque is basically Vs by Km phi minus Ra divided by Km Kt into phi square into T. Okay, now at no load, that is torque is 0, current is 0, so this is the no load speed n naught. Okay, this can be proportional to omega as well, same graph will be same. So what we are observing, if I keep on increasing my torque, it is just like a no load speed is this, right, and then it is linearly decreasing. So it would linearly decrease. It would linearly decrease, right? If, first of all, if armature reaction is neglected, if I neglect the armature reaction, okay, here draw this, armature reaction is neglected. Now I will assume armature reaction to be present, okay, because if torque is increasing, of course the load current will increase, right? Here if torque increases, load current will increase. If load current increases, what will happen? If load current increases, then the flux will reduce due to armature reaction. So if torque increases, I know that load current has to increase no matter what, then the armature reaction will increase, then the flux will reduce. If the flux reduces, what will happen? This value will increase, this value also will increase at a much higher rate. So basically this is proportional to 1 by flux and this is proportional to 1 by flux square. So I will just give you an example. Let's say previously this was 1 Weber, so now due to armature reaction it is 0.9 Weber, right? So what is this value? Previously let's assume the value was 1 by 1, so 1 was the previous value. Here as well the 1 was the initial value. Now if it has changed to 0.9, what is the value here? It is 1 by 0.9. So it is roughly, I guess, 0.99, something like that. 0.9, so 1.11. And here what will be the value? So 0.9 whole square in inverse 1.23. 1.234. So you see, right, the increase in this equation is much higher than this because it is phi square. So this will increase much higher. So basically what is the significance? Significance is that if I am showing a one arrow increase here, then this will increase twice the arrow. This is increasing more. If this is increasing more, that means the speed will reduce because I have a negative sign here. So previously, if my line was here with armature reaction neglected, the line will be somewhat lower with armature reaction considered. So line will be somewhat like this, okay, will be lower. So with armature reaction considered. Okay, so this is basically the characteristics of shunt motor. Okay, we have already done the characteristics of a DC shunt motor. So for a DC shunt motor, the speed variation from no load to full load is minimal, because we have already derived the load speed characteristics with armature reaction considered and ignored. So I don't need to explain here much. Whatever text is written, you can go through it, but already I have explained all the graphs, right? This is the speed torque. So basic equation, how you do the basic equation, from there you can directly find out the speed versus armature current graph, right? I don't need to explain much here, already everything is explained here. Now torque speed, torque current also we have discussed that what equations you need to follow. So I will just copy and paste the graphs over here, that's it. Other things already has been discussed. Speed torque will be similar to torque load, but with armature reaction considered, it will lie lower. Okay, that is the important point. Armature reaction considered, the graph will be lower than the armature reaction neglected, right? Okay, so what are the key observations, like where can I use my DC shunt motor? So my DC shunt motor will mainly be used in case of where speed has to almost remain constant. If I observe that with change in load, speed is almost constant, of course there is variation. You can see in series motor it will be far worse. Okay, but wherever I need constant speed operation, I will use DC shunt motor. And stable and predictable performance, suitable for applications needing constant speed. So with load current, I see that if the load current is increasing, so is the torque. That means if I increase the torque, so it will take more load current, so it has suitable operation. And in case of torque speed, so with increase in torque, the reduction in speed is very lower, so it is very suitable for high torque applications. So stable and predictable performance, the no load speed is saved, and it is safe for stable operation. In DC series motor, you will see we will not be able to operate our motor in no load. Why? I will explain. Okay, the no load speed is safe and operation is stable across load range, suitable for applications needing constant speed under varying loads such as fans, blowers and lathes and conveyors. Okay, this is where my DC shunt motor is suitable. Now we will discuss about DC series motors. So let's discuss about DC series motors. So in case of series motors, the first thing is, will I be able to operate it at no load? Is it possible for me to operate at no load? Okay, so if I write down the equation here, same equation, right? My like basically if I write the KVL, so my Vs or Vt terminal voltage will be equals to Eg EB plus IA into RA plus RSE and my IA is basically IA is equals to the field current IF. IA is equals to the field current IF. Okay, here the important point to note here is that, again, what is the speed equation? Speed EB is again proportional to flux and this, right? So it is basically some km phi n. So I can write here the speed value will be equals to Vt, like 1 divided by km phi Vt minus RA plus RAC. Okay, now you might have a doubt that what if we operate our DC machine at no load? At no load, the armature current is 0, so the field current is 0. So whenever there is 0 field current, what happens? Residual flux. And generally this residual flux is very low, very low value. Okay, very low value, like 0.1 or something, right? So if this residual flux is very low value, and okay, sorry, this is IA into RA plus RAC, right? If the residual flux is very low value, then what happens? This is 0 because I have no drop because Ia is 0. So it is Vt upon very low value. So basically at no load or at low loads, right, N is proportional to 1 by flux at light loads. So basically what happens, this shoots up very high. Previously the flux was not, previously in the shunt machine the flux is not a function of load current, it was constant value. But here my flux is a function of load current because the field current is equals to the load current, that is the armature current, right? So not the load current, the armature current. Okay, so that is the important point that you have to note here. So as at light loads, so my speed both depends on the flux changes as well as the current. So for light loads, right, this drop is very low value, this drop, because RAC is also very low and RA is also very low. Light load speed is inversely proportional to 1 by flux. At larger loads, what happens, the basically this will be, at larger loads speed will be proportional to both, inversely proportional to both the flux, and also it will be proportional to Vt minus Ia Ra plus RAC, right, because Ia is there. So if Ia is changing for large values, it will vary along that. So basically what will happen, then this Ia will be dominating, then this will be dominating basically, right? For larger loads this will be dominating for large loads, this relation will be dominating for large loads. Okay, and for light loads this relationship will be dominating. So for light loads speed reduces. So for light loads the graph will be what, it will be just like a rectangular hyperbola, right? It will be just like a rectangular hyperbola. Okay, sorry, I made a mistake here, sorry. This load current will increase but still Vt will be very high. Yeah, we can see it, yeah, we can see that as well. I mean for higher loads, right, for higher loads as well, this phi will also increase very high, right? So ultimately this is also telling that your speed is reducing, like this equation is also telling you that speed is reducing because Ia will increase, so Vt minus this will reduce, so speed will reduce, and this first equation also is telling the speed will reduce. So ultimately speed anyways is reducing. Okay, and this is known as linear reduction. In this region there will be linear reduction because this will be dominating, and initially it will be rectangular hyperbola. So the graph, the speed versus load current graph will be somewhat like this. So it will be rectangular hyperbola initially, then it will be linear. So in this region this will behave like a rectangular hyperbola because it is 1 by phi, that is a graph for rectangular hyperbola. And this will be linear reduction. Okay, for higher loads. So all this we discussed with armature reaction neglected. Now this graph was with armature reaction neglected. If armature reaction is considered, what will happen? Basically, the graph will shift up, right? If armature reaction is considered, graph will simply shift up, correct? So yeah, that is what will happen. So if I consider armature reaction, what will happen? The overall flux will reduce. So if the overall flux reduces, what will happen? Then the increase in flux, right, will reduce, hence the speed will increase. So overall graph will shift up basically. So this will be the same graph only, it will be shifted up. So I will draw this. This is without this is armature reaction neglected. So with armature reaction, the graph will be simply shifted up. So shifting due to reduction in flux. Okay, so this graph is with armature reaction considered. Okay, so yeah, I hope you have understood this basic speed current characteristics. Now let's discuss about the torque speed characteristics. What will happen with the torque speed characteristics? Okay, so in case of torque speed, right, so what is my torque proportional to? Phi into Ia. So my torque is equals to kt into phi Ia, right? And in case of a series generator, I know my flux is proportional to the field current, which is proportional to the armature current, because the field winding and the armature are in series, right? So basically I can write here that my T, right, is equals to oh sorry, I should have not written it over here, that my T actually is proportional to flux is proportional to armature current, so it will be Ia square. So roughly my torque will be kt into Ia square, right? So it will just be a parabola, it will just be a parabola, that's it. Okay, so your torque current characteristics will just be a parabola. Now at higher loads, if like it will be just be a parabola if saturation is ignored. So I will discuss about saturation, all those things I will discuss, right? So if I draw the graph, so this is my load current, armature current, and this is my torque, right? So it is just like a parabola. The parabola is somewhat like this, correct? Keep on increasing. Now this is the case when armature reaction is not considered. If armature reaction is considered, then what will happen? The flux will not increase so much. So if flux is not increasing, so this torque will not increase that high. It will increase, but it will not increase that high. So graph will simply shift down. So this is the armature reaction and saturation. So previously as well, one more thing I have to discuss. Uh, like okay, also one more thing, at higher loads, right, I forgot to mention, at higher loads flux will almost be constant. Why? Because what is the BH curve? I forgot to mention this. So BH, right, so this is the BH curve. So at higher loads, right, flux is almost constant. Higher loads, due to saturation, flux is almost constant. So if flux is constant, it does not depend on this, right? It only depends on this only. That's why this is dominating for large loads. Got it? So this will all be a linear direction because this will be dominating for large loads. Okay, here as well, if I assume saturation, right? This is without saturation. If I consider saturation, then what will happen? If I consider saturation, then right, for higher loads, the torque will linearly vary with flux, right? So initially this will be like this only, okay, it will be parabolic, but due to saturation it will just vary linearly, it will not vary parabolically. Okay, so this region will be the linear region because why? So here, right, armature reaction and saturation neglected, and here the armature reaction and here the saturation is considered. And if I consider the armature reaction, then the increase in flux, right, in this region will be far lower, right? So it will not be higher. So graph will, the torque increase will shift downwards basically. So this graph will be the graph with, so with armature reaction considered, the graph will just shift downward and then ultimately it will be totally linear. So this is the graph with armature reaction and saturation considered. Previously we were not discussing about saturation because the flux was constant. Now the flux is varying, so flux can be saturated in this case, right? Again, we are not discussing about the no load because if flux is 0, it will be very high speed. That's why we are not discussing about no load, right? So rectangular hyperbola is discontinuous about x equal to 0. Now let's discuss about the speed torque characteristics. What will be the speed torque characteristics? So if I discuss about the speed torque characteristics, what is the speed equation? So same thing, right? Speed equation is this one, right? This is the speed equation. And what is the torque equation? Torque equation is this, right? Ia square, correct? Kt into Ia square. So I can replace my Ia with 1 by under root Kt, correct? So basically here Ia will be torque like whole under root T by Kt. So N is basically 1 by K m phi. Okay, Ia is also this. Okay, Ia is here as well, right? So this will be 1 by basically phi. Okay, because flux will change, right? I have to directly write in terms of Ia only. My flux is also proportional to Ia. So what will be my flux here? So basically flux also will be some constant K1 into T divided by Kt. Let me write this K phi into T divided by Kt, right? So this will be K phi under root T into under root Kt. I just want to write the equation. Okay, so here this into Vt minus Ia. So Ia is this value again, that is T under root by Kt into Ra plus Rac. So this will be equals to, if I want to write this further, this will be equals to, this is some constant, right? Constant and under root T is there, that will vary into Vt. Vt is also constant. So it will be some K prime into Vt, sorry, into divided by under root T, okay, minus, remember this torque, this under root T is automatically getting cancelled, this KT and KT also is automatically get cancelled, this RA plus RAC is constant, this Km K phi is constant, so this is K double prime, right? So basically when I am trying to plot the speed torque characteristics, it is just a square root, like my speed is inversely proportional to square root of the torque, okay, speed is just inversely proportional to the square root of the torque. So I can say here my speed is inversely proportional to square root of torque. So how will the graph look like? So graph also is almost like rectangular hyperbola only, but not exactly like a rectangular hyperbola, okay, graph will not be exactly like a rectangular hyperbola because it is not inversely proportional to torque, it is inversely proportional to 1 by torque, so it will be like a hyperbola. It is the equation of similar to a hyperbola, okay. So similar to hyperbola, this color will be white, okay. So speed and torque, speed and torque, okay. So it will be just like a hyperbola. So here the reduction will be somewhat like this, and what happens at higher speeds, at higher load currents, if Ia is very high, right, then the flux is constant, then the flux is constant, if the flux is constant then only we vary with Ia, and Ia is equals to under root of T, right. So at higher values, for higher torque, if torque is high, then load current is high, if load current is high then the flux is high. So at higher torques, at higher torque levels, right, the Ia will be very high, if Ia is very high then flux will be constant because we will assume saturation, right. And if I consider armature reaction, what will happen? Armature reaction, if I consider, flux will reduce further, so it will not be exactly proportional to under root of torque, it will be slightly lower. So basically so torque also, this will be also somewhat lower value, so it comes in the bottom here, so speed will slightly increase. So roughly our graph will be somewhat like this, okay. So for higher values my speed will be proportional to under root of torque, for lower values of torque speed will be inversely proportional to under root of torque, okay. This is for the lower values, this is for the higher values, that's it. This is the speed torque characteristics, okay, and this is known as the hyperbolic curve, right, hyperbolic curve. So these are the different characteristics. So these are the basic equations that we discussed. At low speeds flux is small, so speed will be very high. As Ia increases, flux increases, speed also drops rapidly, okay. So this is the speed armature characteristics that we have discussed here. Let's now discuss the torque armature current characteristics. So torque armature current characteristics is here, okay, already has been discussed, same thing has been written over here. And the speed torque characteristics will be hyperbolic, this will be the speed torque characteristics. So these are the characteristics that the motor, series motor, will have, okay. So we never operate DC series motor without load because it will run at very high speed that can damage things near it, right. So produce very high starting torque. Starting torque also will be very will it be very high? Produces very high starting torque. No, right? Because torque is proportional to speed. No, this is wrong. At no load, no. This statement is wrong. It does not produce high starting torque because uh, produces very low starting torque which increases rapidly with current because it is proportional to current square. So actually, it initially produces low starting torque, then it increases very rapidly. Okay, so it is not very high, produces low starting torque. So which increases rapidly with current. Ideal for traction systems, cranes, elevators, where high, okay, so it is a bit wrong here. It should not be initial, it should be high torque is required, because of course initially it will produce zero torque, but as the it will demand more current, so torque also will be increased, right? So it can produce more torque with increased load. So in elevators and lifts where the load is higher, so as the load current will be higher, torque also will be very high because torque is proportional to current whole squared. So torque also it can provide high torque. So that is why it is ideal for these kind of applications. Now what are the problems? Problem is poor speed regulation. Speed drops significantly with load. If you see, if I increase my load, speed is dropping by significantly, right? Huge significance drop there is in speed. But in case of shunt machine, there shunt motor, there was not this much amount of drop. So there is poor speed regulation. So what is the formula for speed regulation? Similar to voltage regulation, speed regulation will be n no load speed minus n full load speed divided by n full load into 100 percentage. Okay, so this is the speed regulation, and we must not operate the motor in no load because there will be risk of over speeding. Okay, we must not do this. So these were few points regarding the DC series motor. Okay, I hope you have understood all the things. Now let's discuss about the compound motor. So if I discuss about the compound motor, what is the equation in a compound motor? So compound motor basically will combine both the series and the shunt field characteristics. Okay, so let me here copy few graphs. Let me copy the series one. Let me copy the shunt one. Shunt speed. Okay, I have to copy everything, right? That will be time consuming. These are the shunt, right? Shunt characteristics. And the series characteristics. Series characteristics are this: speed, torque, and the other two, torque, speed. So in case of a, let's do for a cumulative compound motor, right? Let us do for a cumulative compound motor. In case of cumulative compound motor, ultimately what is the flux equation? Flux equation phi equals to flux shunt flux plus series flux, but this is constant, right? Because Vt is constant. Vt is constant. So If also will be Ish also will be constant. Okay. Ish also will be constant. So ultimately, right, series flux is there, but initially this time, if the load current is 0 or if Ia is 0, the phi will not be 0 because phi will be equals to phi sh. Previously the series winding was going down, but it will not be 0. So the no load characteristics will be similar to the shunt generator, right? So if I superimpose, right, if I want to superimpose my graph, the speed load characteristics, right, load speed characteristics, this is I A, this is N. So in case of, this was the case for shunt generator, right, with armature reaction considered. This was the shunt generator, not generator, motor, and this was the series motor characteristics. Correct. So initially the speed will be very high, right? Initially the speed will be very high. So cumulatively will be somewhere in between. So cumulative compound motor will be just like this. So no load will just be same as shunt because no load flux will be same for both of them, and after that it will drastically reduce basically. So this will be the cumulatively compound DC motor characteristics. Okay, and this is the series one. Okay, understood. So this was the speed load characteristics. Now what is the torque speed characteristics, right? Again, let me go back and understand in equations what will be the torques. Okay, why is this everyone coming in? Okay, let me change this. Yeah, let us discuss about the torque speed characteristics. So again, equation of torque, right, will not change. That will be a constant equation. That will be a constant equation. So this is torque load characteristics. So in case of a motor, torque is proportional to flux into current, right? So flux is this time phi sh plus phi ac. So this time, right, at zero current the flux is not zero, flux is non-zero at zero current, but as current is zero, torque will be zero, right? So let me again copy and paste the torque speed characteristics of both the machines. So this is the first one, shunt one, and this is the series one. Okay, so this is the series one. So compound, right? Again, somewhat it will be in between. It will be better actually, because in case of shunt, what was happening? There was saturation. We were reaching saturation, right? But in case of compound, even though at lower loads, if let's say at lower loads, if IA is low, then flux will be approximately equals to the shunt flux, right? Because the series flux is proportional to the field current, series field current, which is in turn proportional to the armature current. So if IA is low, then the series field also will be low. Now if IA is high value, if IA is high, right, then the flux is what? Flux will be approximately equals to phi AC, because the series flux will be very high, but it also will reach saturation, but its saturation will be later because it is both equals to phi AC and phi AC, right? And shunt flux is almost constant, right? Because it does not vary with load current. So basically what will happen, it will just follow at for lower values of load current, it will just follow the linear line about the shunt axis, but it will be slightly higher because the series field is also getting added now. In case of high load current, what will happen? The series field will be dominating, but of course the increase will not be that high because again there is saturation. But as both of these are getting added, so this saturation will be higher than the previous one. So I will get higher torque than the previous one, right? So this will be the DC cumulative compound motor. Okay. Now let's discuss the speed torque characteristics. What will happen with the speed torque characteristics? So this is the uh, this is the speed and this is the torque, right? How does my motor depend on the speed torque characteristics, right? So in case of, again, how is the torque dependent? So torque is again proportional to flux into armature current, and speed again is proportional to Vt minus IARA divided by flux, right? This is what my Vt was proportional to, if you remember correctly, right? So if I replace here, so my speed will be equals to some constant 1 by k phi into Vt. What is Ia equals to? So Ia is equals to T by flux, Kt into T by flux. So this will be Kt into T by flux. Okay, so ultimately my speed is equals to Vt by k phi minus Kt into T by phi square, and K is also there, right? K phi. Okay, this let me write this as K only. Okay, phi, K into phi. Okay, so this is the equation basically. So what do I observe? I observe that it is proportional to the flux square, right? And this is basically what. So it is like a parabolic curve. It will be just like a parabolic curve, but its phi square has negative coefficient. Its phi square has negative coefficient, right? So basically, if I copy the torque speed characteristics for a shunt motor, here and here. Okay, we have to change the color. This color won't work. This color is not. DC series. This is DC shunt. Okay, so roughly the cumulative compound will just follow the shunt one, right? Because this is the equation that we get while solving the shunt. If you remember, this is the equation that we get while solving the shunt one. But here, as previously in case of shunt, right, in case of shunt, if you remember, in case of shunt, my flux was equals to phi sh, but now in case of compound generator, my flux is equals to phi sh plus phi ac. So it has increased now. So there will be further reduction because this phi square will be more dominating. There will be further reduction. That's it. That is the only difference, except that the graph will not change. So basically, it will, the no load speed will be same here. Okay, it will not be different because the at no load the armature current is 0. So this phi ac is 0. So only phi sh is present. So it is same for both shunt and the compound machine. So we will start with here, and just the graph will be shifted down as my cumulative compound, as my flux has went up. That is the only reason basically. Okay, so yeah, these are the basic characteristics of a cumulatively compound machine. Important fact to note here, if I observe that shunt machine, right, if I see here as well and if I see here as well, that shunt machine has better speed regulation. Shunt has better speed regulation because the reduction in speed is lower for shunt. So shunt motor has better speed regulation. Okay, now we want to discuss about differentially compounded, right? What will happen to differentially compounded? So for differentially compounded, right, the relation will be same, just it will be opposite. What do I mean by it? So this was about the cumulative compound motor. Now let's discuss about the differential compound motor. So for differential compound motor, I will copy the graphs. Okay, I'll copy this graph. I'll copy everything. Okay, all the analysis will be similar. Just overall flux will be phi sh minus phi ac. So this will become negative here. So what will happen? The flux will reduce, and if the flux reduces, what is my speed proportional to? Speed is inversely proportional to flux, right? This is the relationship. So if my flux reduces, because here the flux will reduce, the speed will increase. So at no load, it will be same as the series one because phi ac will be 0, but as the load increases, phi series will increase, hence the flux will reduce. So speed will increase. So the equation will be somewhat like this. So this will be the differential compounded. Of course, there will be saturation. After that, the flux will not increase further because it is negative here, right? So this is the differential speed current characteristics, and after this point, right, after this point, at this point we reach in the unstable region. So this region is known as the stable region, where the machine can operate. Like actually the graph is like a cup. To be honest, the graph is like a cup, because okay, initially, yeah, so what I can say, I will discuss that. So initially, right, initially phi AC is very low compared to phi AC, right, when my IA is low. Hence, it will just behave like a shunt machine. In a shunt machine, what happens? The speed reduces. So this also will reduce its speed, but it will reduce more. Why will it reduce more? Because here there is subtraction. Sorry, this flux phi SH will increase, and this also will increase. Right? Both of them will increase, but this will increase. Sorry, this will be constant, and this will increase very slightly, but it does not matter. This will be almost constant. So okay, this will be okay, speed if the load is increasing. Okay, sorry. So also, right, there is another relationship. So speed is equals to Vt minus IARA. Vt minus IARA. Vt minus IARA divided by phi. So what happens if the load is increasing? So there is very little change initially. So flux initially is constant. Phi SH initially is constant. Constant. Phi SH is initially constant. So my overall speed, right? Overall speed will be proportional to Vt minus IRA. So what will happen? IA will increase, so my speed will reduce. So that's why initially the speed will reduce. Now after a certain point, what will happen after a certain point? That now the phi AC will not be low anymore. Phi AC will be significant because the load current has increased. So now I observe that although the numerator is decreasing, right? This is the numerator, this is the denominator. That is what my speed depends on. Although the numerator is decreasing, so is the denominator, and denominator will decrease more rapidly. So after a certain point, what will happen? There will be unstable region. In the unstable region, what will happen is the speed will just keep on increasing. Why? Because the flux will just keep on reducing. So this is the region for which the motor is stable. So this is known as the stable region. Stable region, and after this whatever comes up, right, is known as the unstable region. Why? When the load current IA is high, that means my IAC, series field current, will be high. That means what? That means the that means what I can say is my what I can say, series field current will be higher. So overall flux, right, is equals to phi SH minus phi AC, and this is constant. It is Vt by Rf. This is reducing. So sorry, this is increasing, right? So overall my flux will reduce rapidly. Rapid reduction. So my speed will increase rapidly. Okay. So this becomes a positive feedback, because load current will keep on increasing, speed also will keep on increasing. So this becomes a positive feedback, due to which basically the machine will go into unstable run away. This is also known as unstable run away. Okay. So now let's discuss about the torque current characteristics. This was the speed current characteristics. So if I just copy the torque current of the previous graphs, so I'll copy everything. So for torque current, right, we have to assume which one is dominating first. Okay, so in case of differential, it should be mentioned which flux is dominating. So our assumption will be that the shunt flux is dominating. Okay, so IA equal to 0, shunt, sorry, not IA equal to 0. So for low value of IA, phi SH is dominating. Phi SH will be very high than phi series, or basically shunt flux is dominating than the series one. Okay, so now this time my flux will be phi SH minus phi SE. So the torque speed characteristics will be something like this. Initially, if phi SH is 0, it will be proportional to phi SH. So torque will be phi SH proportional to IA, and phi SH is assumed to be constant. So torque is proportional to current. So initially it will vary like linearly. Then what will happen? Then the series flux will be significant, right? Series flux will be significant. So my flux will be phi minus phi SH minus phi SE. So what will happen? Ultimately the flux will reduce. So here also something like this will happen, right? Initially it will reach a peak point. After that the flux will reduce. If flux reduces, what will happen? Even though the load current is increasing, the torque will reduce by a further amount. So here, even though the flux was reducing, but the current was increasing at a faster rate, that's why still my torque was going up. But after a certain point, what will happen? Even if there is an increase in load current, flux will reduce very high amount. So overall torque goes down. So this torque goes down, goes down, goes down, and it becomes weaker and weaker. So here that is what happens, and after a certain point it crosses the threshold. So this point is the point where my phi SE will be greater than phi SH. So the flux becomes negative and torque is proportional to flux and current. So current direction will not change. So flux direction has changed, it has become negative. So torque direction also will be changed. If torque is negative, it will rotate in the opposite direction. So that's why the torque is negative here. Okay, so this characteristics is for that where the shunt field is much weaker actually. Okay, if the shunt field is much weaker, right, this characteristics was for that. If the shunt field is weaker than series, then of course the torque direction will change. Okay, but what if I assume, that the shunt field is always stronger than series field? Okay, shunt field is always stronger than series field. So in those kind of cases, what will happen is, although here also there will be reduction in the torque, but not that high. Okay, also the direction won't be reversed now. So basically what will happen now, so in this case it will increase. So what will happen here is that, it will increase, then again it will reach a point where the increase will be lower than the decrease of the flux, increase of the current will be lower than the decrease of the flux, so it will just die down like this. So here the shunt phi sh is much larger than phi series, and hence whatever is the increase of the current, right, that is not sufficient to change the direction of the torque. Okay, now what is the speed torque characteristics? So what will be the speed torque characteristics? So if you remember, what was speed equals to? So what were the two fundamental equations? Two fundamental equations: torque was proportional to phi into Ia. Okay, so torque is equals to Kt into flux into Ia, right? And another fundamental equation was my speed was proportional to Vt minus IaRa. It is basically Eb divided by the flux, or I can write N is equals to K, whatever you write, whatever constant, does not matter, IaRa divided by flux. Okay, so what I can do is I can replace this Ia from here, right? I can replace this Ia from here, so my speed will be equals to K, will be anyways outside, Vt by phi will be there, minus Ia will be replaced with T upon Kt phi. So this will be T, IaRa will be there, let me name it as K prime. I like Ra is a constant, right? All whatever constants there are, I am just naming it as K prime, T upon phi, and already a phi is there, so that will be phi square. So it is basically, if I copy the speed torque characteristics here, so initially, right, what is my flux and what is my torque? So initially, if I see my flux, right, flux is what, phi sh minus phi ac. So initially again we will follow our shunt machine only. So initially we will start from the same point, same N naught here. After this, what happens? If the torque increases, if the torque increases, the load current will increase. If the load current increases, the flux, series flux will reduce. So overall the flux actually reduces. So if the flux reduces, so this one will also be higher. This one, if flux reduces, this will increase overall, and I have a negative sign, so overall speed reduces. So that's why the speed will initially reduce, and then what will happen? After a certain point, it will go into unstable region, because what will happen after a certain point, if torque is increasing, phi series will keep on increasing. So basically my flux, right, will be proportional to negative of phi series. So if it is negative of phi series, right, so then the series flux will be dominating, so shunt flux will go away. So this, right, this is positive because it is T upon phi square. So this thing is positive, so I have a negative sign over here. So overall this will be negative, right? And again Vt upon phi itself is negative, so this is also negative. So what is happening? Speed is trying to go to negative. Okay, but okay, there are two cases here. Either speed will go to negative or positive. So but we will assume the case where the, okay, we will not assume this case, we'll assume the case where my shunt shunt flux always will be very higher than the series flux. Okay, series flux will never go beyond shunt flux. Okay, assumption. For that only we will derive our expressions. Mainly that is the practical case as well. So in that case, this will keep on reducing after a certain point. Okay. Basically my flux will be saturated, right? After a certain point flux will be saturated. So I'm just trying to figure out. Okay. So this basically after a very high increase in current, IF very high. If IF is very high, then my flux, right, overall flux will be very low because phi is phi SH minus phi AC. So overall flux will be very low, and I know for very low flux, right, speed goes to unstable region. It goes to unstable region here, right, for very low flux. Okay, this we have already previously discussed. So it will go into unstable region. Basically what will happen, this will just increase. This will be similar to the speed current characteristics. Okay, so this will be the again the unstable region. Where flux is very low. Okay, so that is a disadvantage basically of a DC shunt DC differentially compounded machine. Okay, so a compound motor combines both shunt and series winding. Cumulatively compound series field aids the shunt. Okay, differentially series will oppose the shunt. Cumulative compound provides better starting torque than shunt motors. Why? Because both the series and the shunt field are aiding each other, right? If you see here, that cumulative compound will provide better initial torque, will be very better. It is higher than the series and the shunt because it combines both of them, right? And with improved speed regulation over series motor. If I see, speed regulation is also better for cumulatively compound motor. If you see here, the like than series it is better, right? Of course, than shunt it will be lower, but the torque provided by cumulative is better. So there is bit of trade-off, which one you want. So now let's discuss about the differential one. So differential motors are rarely used in practice due to instability and operational challenges. Okay, already we have discussed, right? There is some unstable region, and we would never want our motor to operate in the unstable region. By some fault or some working of the user, if he takes the motor into unstable region, I won't be able to reach there and fix it, right? So we generally avoid using differentially compound motors. So in differentially compound, series field opposes the shunt. This oppose reduces the net flux, armature current increases, leading to instability. So at when motor speed n is 0, then there is some back EMF is 0, right? So initially, right, if the motor speed is 0, motor speed is not rotating, that means the speed is 0, that means it does not matter whatever is the flux value, the EB will be 0. If EB is 0, there will be huge current IA flowing. IA will be what? VT by RA, correct? IA will be VT by RA. So this is very high current, right? RA is very small. RA is like roughly 0.1 ohms, 0.1 to 0.5 ohms. Okay. Now, so IA will be very high. If IA is very high, IF also will be very high. That is, I series will be very high. If I series is very high, then the flux will reduce. So basically, the speed will go very high. So very high starting current it will take. EB begins to build up, opposing the supply voltage. Flux keeps decreasing due to opposing series flux. EB may never stabilize because the speed is increasing at a very fast rate. The direction of torque keeps on reducing, because what happens if, let's say, if the field current is very high, and if for some reason the shunt flux is not enough, then the overall flux will go in the negative direction, and if it goes in the negative direction, there may be problems. Okay, So the direction of the torque keeps reversing. The motor may fail to start. There may be a failure to start because for certain second the direction of the torque will be negative, for another second direction of the torque will be positive. So it keeps on reversing, right? So thus it's not a self-starting motor. It is prone to hunting and reversal of motion. And initially also there is huge starting current that can also, it can go into the unstable region initially. Okay, that's why we generally tend to avoid the motor, okay, because the flux direction keeps on changing. Okay, so that is the thing. So again it is unstable at light load, it is unstable at zero load, no load initially at starting, it is unstable at starting, and it is unstable at high loads. At high loads, if armature current is very high, again the series flux will be very high, again there will be net flux reversal, motor may rotate in the wrong direction or it might go into the unstable region, right, that we have already discussed. Okay, so these are the things basically, and this is the summary where you can use each shunt series differentially compound motors. Now let's do a few questions and try to solve all this, right, whatever we have understood, try to implement that. So a DC series motor is operating from its rated supply voltage and is subjected to overloading. Okay, DC series motor is there, it is subjected to overloading causing saturation of its magnetic circuit. Under these conditions, which of the curves in the figure most accurately represents its torque speed characteristics? So torque speed characteristics, if you remember, if it is reaching saturation, right, so I know that again torque, okay, so torque is proportional to flux into Ia and my speed is proportional to Vt minus Ia Ra divided by flux basically. So torque speed is the most difficult one and that is the most important one, so to remember, right, so always try to go with basics. So here if I say that for lighter loads, right, torque will be proportional to flux square, correct. Basically my Ia is proportional to flux, right, when my Ia is low, basically saturation is not happening. I will discuss about the saturation part. So then what will happen here, then basically I can say that this speed will be basically this Vt divided by phi minus Ra basically. Okay, why? Because here current is proportional to flux, right, because field current, series field winding current and the armature current are same, so both of them cancel out. So basically it will initially be a like a rectangular hyperbola. It will be like my speed is inversely proportional to flux. And okay, what is my torque equals to? Okay, so my torque, right, okay, torque is equals to flux whole square. So flux is proportional to under root of torque, so I can write here speed will be 1 by speed will be proportional to 1 by under root of torque, right, initially. So the graph only this one is the correct one, this one is the correct one which I can see. Okay, and okay, sorry, this one is the one. And then at uh, higher loads, what is happening at higher loads, if I remember, the flux is getting saturated, so my torque only will depend on the armature current and my speed also will only depend on the armature current, that is minus T into Ra, right, because the armature current is proportional to torque for higher loads. Okay, okay, let me just read this. Okay, let me read the question properly. A DC series motor is operating from its rated supply and is subjected to overloading. So actually we are overloading it, we are not operating at low value of current. Okay, so not operating here, right. So if we are overloading it, overloading means my Ia will be greater than Ia rated, right. So Ia will be greater than Ia rated, that means automatically we are in this zone only, automatically the series field winding is saturated by default. Series field winding is saturated. So if you did this analysis, right, you are wrong. If you thought of this and you thought that C will be the correct answer, then you are absolutely wrong. Okay, because read the question, what have they told. So series field is already in saturation. So if series field is already in saturation, so my current will be directly proportional to torque. So my speed will just be a linear relationship with negative slope. So if I see, only the option B has a linear relationship with negative slope. So option B will be correct and not C. Just be careful here, right? Just be careful. So linear with negative slope. Okay. So I hope you have understood this basic point. So what is the next question? A differentially compound motor is equipped with interpoles and brushes set on the neutral axis, is to be operated as a generator in the same direction of rotation with same terminal voltage polarity. Under these conditions, it will behave as what? Okay. So again, we have to, like, this kind of question we have already discussed. So I will again take the circuits, right? So I have a differentially compound motor equipped with interpoles and brushes. So it has interpoles and brushes at neutral axis. So if it has interpoles and brushes, basically if it has interpoles, so I can assume that armature reaction is non-existent. So let me just do this. So for a motor, right, uh, poles and brushes on neutral axis. So if you remember one thing, that for a motor, in case of a motor, let me draw a few things. If it has interpoles, right, so let me assume a two pole machine. So this is the north pole, this is the south pole, this is the armature, this is the motor. Now here I will have interpole here, and here I will have interpole in the bottom, right, along the GNA or along the MNA. Now tell me, what will be the polarity of the interpoles? So the polarity of the interpoles in case of motor will be same as leading poles. If I assume that my motor is rotating, right, in the clockwise direction, so here the polarity will be same as the leading pole. So this will be south pole, this will be north pole. So this will be my interpole winding basically. Got it? Now what are they discussing? Now, okay, and this is my motor, right, and this is my generator. So in case of motor, the current direction are like this, right? This is the current direction, ISH is here, IA is here. So in case of generator, the IA direction changes, hence the series winding direction also will change, right? So previously overall flux was phi SH minus phi SE. They should have mentioned here that the shunt field is dominating, should have been mentioned. So here in this case, if you see that the shunt field winding current direction has not changed, but the series field winding current direction has changed. It was previously going from right to left, now it is going from left to right. So the direction of the series field winding has changed. So the flux also direction will change. Phi C. Okay. So this will be phi SE. Now, okay, with this, like, if the direction, if I am working it as a generator and rotating in the same direction, it is rotating in the same direction. What are they asking? So now this is working as a generator. So let me reduce the size of this. it functions as a cumulatively compound generator, but the interpole coils must be reversed. So will the polarity of interpoles be like this? No, right? Interpoles cannot be like this, right? Because in case of generator, it should be opposite of the leading poles. This we have already studied, right? It should be opposite. Actually, we have done this kind of question, right, previously. So yeah, in case of interpoles, right, interpoles have to be changed, but flux automatically is working, so it will not remain as differentially compounded, it will become cumulatively compounded, but the interpole coil must be reversed, right? Interpole coils must be reversed. Option B will not be correct, that it will work as a differentially compound cumulatively compound DC motor without reversing the interpoles. That is incorrect. We have to actually reverse the interpoles coils. So option A will be the correct one here. Option A will be the correct one. Okay. So yeah, I hope you have understood this basic points. One more thing. Sorry. Okay. I made a mistake, right? So yeah, this should be North Pole and this should be South Pole. But remember, this current is taking from what? Current is taken from the brushes, right? So previously, if you remember, okay, this is not directly here. If you remember, previously the current, it was working as a motor. Okay, I was again making a mistake. It was working as a motor. So if it was working as a motor, then the armature will take in current, right? Now it is working as a generator, so the armature is giving current. So automatically the field will get reversed, right? How? So it's just like if I have a coil here, I think we have already discussed previously this, right? If I have a coil here, right? If I have a pole here and winding orientation, I'm not changing, right? Winding orientation, I'm not changing. So current is flowing like this previously. So what is the field direction? If I see, the field direction is along the left hand side according to the right hand rule, right? Now for the same pole, if the current direction has changed, winding orientation, of course, I will not change. Physically, I cannot change the winding orientation. If it is coming outwards now, what will be the direction of the flux? It will be on the right hand side. So it will be on the right hand side. Okay. So basically, previously, if this was south pole, it will become north pole. That's it, right? Because south pole takes in the flux and north pole gives out the flux, right? So automatically the interpoles have reversed their direction. So actually this is incorrect. So interpoles as armature current direction has changed, so the interpoles also will automatically be reversed. So we don't need to do anything extra additionally, right? We don't need to do anything additionally. Okay, that is a very basic thing. Okay, this we have actually discussed previously. So this is the interpoles, how what are they done and what happens basically. Okay, yeah. So now let's do the next question. So the direction of rotation of DC series motor can be changed by doing what? So if you remember, how can I change the direction of rotation of a DC series motor? So for that, I will need to write the equation of torque, because torque, if it is positive, it will rotate in the clockwise, if I assume positive to be clockwise, and if it is negative, it will rotate in the anti-clockwise. So torque is proportional to flux and I, right? So in case of uh, series motor, flux is proportional to IA, correct? Flux is proportional to IA. So I cannot directly reverse the direction of torque, because it is proportional to square, because it is proportional to the square of it. So how can I actually reverse the direction of the torque? So if I draw the circuit, so ultimately what we can do is keep the, look, like this is the terminals of the armature A1 A2, okay, and this is the terminals of the field winding F1 F2. So currently, so what ultimately what we have to do is, we don't have to go by this relation, we can cancel this relation. So this is the field winding F1 F2, and this is the armature winding A1 A2, right? And in both cases the current is flowing from F1 to F2 and A1 to A2. So what we can do, either we can change the direction of flux or change the direction of current, but not both at the same time, right? So what we can do is, we can change the connections of the series field. So we can connect the F1 to A1 now. So what we can do is, the F1 can be connected to A1 and F2 will be connected to the supply. So now if we see, now the direction is on the right hand side, it is not anymore on the left hand side. So the field current direction has changed. So IF direction has changed. So IF direction has changed. So of course the flux also will be negative, so the torque also will be negative, right? But I should not change the terminals A1 A2. If I change the terminals A1 A2, then both the current, if I change the terminals A1 A2, same thing will happen, right? I'm not drawing it, same thing will happen, both the current also will change. So either change, either swap terminals F1 F2 or A1 A2, not both. Okay, don't change both. If I change both, then the direction will not simply be reversed. So by swapping the supply terminals, no, if I swap the supply terminals, right, everything will be swapped, right? So this is not correct. If I swap the supply terminals, what will happen? I'll show you. If I swap the supply terminals, basically now this will be plus, this will be minus. So current will flow like this, IS. So it will flow like this, like this. So both the armature current direction and the series flux direction both have reverse. So automatically minus into minus will be plus. So torque direction will not change. So swapping the supply terminals will not help us. By swapping the field terminals, yes. By either swapping the supply terminals or the field terminals, yes. Option C is the correct one, right? Either by swapping the supply or field terminals. By swapping both the supply and the field terminals, this also will work actually. By swapping yeah, this also will work, this also will come, because what am I doing, I'm swapping the supply terminals and I'm swapping the field terminals. So current to the field terminals still remains in the same direction. I will explain you what do I mean by it. So now, right, instead of this being the IS will go from the bottom, because this is plus, now this is minus. So IS will go here, it will come here, IS will come here. But the twist is, I have changed this direction, right? So now this is swapped, and sorry, this will be connected here and this will be connected here. So IS will come here, IS will come here, and IS will flow like this. Still previously, if you see in the first diagram as well, IS was in the same direction. Here also the IS is in the same direction. So is direction does not get reversed, but the IA direction is reversed. So IA direction, this is the option D, IA direction is reversed, but IS series field winding is not reversed. So this also will work. Work like to reverse rotation of motor, right? So both option B, C and D are absolutely correct. Okay, sorry, okay, either way, okay, no, this is the, sorry, I thought this was written here armature terminals. No, this is written supply terminals. I'm really sorry. So no, with supply terminals you cannot do it. By swapping field terminals you can do it. By swapping both the supply and armature field terminals also you can do it. Also by swapping armature terminals. Generally we don't have access to the armature terminals, that's why we generally, that is not present in the option, but this also is a correct answer, by swapping the armature terminals. Okay. If a DC series motor is mistakenly connected to a single phase AC supply, what will be the resulting AC torque? Okay, so if you remember, what is the torque equation? Torque is proportional to flux IA, and if I assume no saturation, then my torque will be proportional to IA square, right? Or it is proportional to phi A square. And they're telling me that I am providing a AC supply. If I am providing a AC supply, that means voltage is AC. That means the generated flux also will be AC only, and torque is proportional to square of it. So it does not matter if it's AC or DC, right? So basically, if my phi A is a sinusoidal, so not phi A, sorry, phi SE, right? Not phi A, phi SE. It is sinusoidal. If I square it, what will happen? This is what my torque is proportional to, right? So torque will be somewhat like this, right? If I square this graph, so basically I'm getting a DC value here. It is pulsating DC. So is it zero? No, it is zero. It is not zero. Is it oscillating? Yes, it is oscillating. Constant in one direction? No, it is not constant in one direction. It's pulsating in one direction. It is actually not oscillating. Oscillating means this. This is what oscillation means. It is pulsating and it is in one direction, unidirectional, because torque is always positive. From the graph I see torque is always positive, so that's why option D will be correct. Okay, it is unidirectional but pulsating. So unidirectional, one direction also can be said as unidirectional. But pulsating. Okay, so let's now do the next question. So in the next question we have to match the following DC motors with their corresponding characteristics. So list 1 and list 2 are labeled. List 2 is 1 2 3 4, list 1 is this. Choose the correct combination from the options given below. So list 1 is shunt motor, series motor, cumulatively compound motor, differentially compound motor. So shunt motor, if I remember, this is what? Torque versus armature current. So torque current. For a series it is like a parabolic, okay, and for a cumulatively compound as well, it will be like a parabolic only. So I observe that 1 2 can be, so for a cumulatively compound the flux will be higher, right? Flux will be higher. So for a cumulatively compound, like flux will be phi sh plus phi se, right? So it will be higher. So as I know, my torque is proportional to phi whole square, because it is a series machine. So because at higher loads it will be like a parabolic only, so torque will be higher for same amount of armature current. So I can see one will be the cumulatively compound that is present in option C and D. So option A and D. So out of these two, something might be correct. Okay, and two will be for the series one. So two, if I see, two is present with B in both these options. Now let me eliminate the 3 and 4. So 3, right? In case of a shunt machine, if I remember, that torque is proportional to flux into current. In case of shunt machine, this flux is constant, right? So it will just be linear. If I assume, if I neglect the saturation, it will just be linear. So 3 will be the shunt. So A will be with 3. So A is with 3 in the option A. So option A will be absolutely correct. Let me go and verify the last one. D is 4. So differentially compound. Again, differentially compound means what? At higher loads, what will happen? At higher loads, flux is phi sh minus phi se. So phi se will increase, right? At higher loads, phi se will increase. If phi se increases, flux will reduce. Okay. So flux reduces, what will happen? At higher loads, torque is reducing sharp, like although the armature current is increasing, but the flux will reduce sharply, so the torque also will reduce. So this fourth one is for the differentially compound motor. Okay, this was the answer for this particular question. Okay, now let's solve this question. What are they telling us? So here a DC over compound generator was properly supplying power to an infinite bus. If the prime mover suddenly stops providing mechanical input, the machine will operate as what? Okay, the prime mover has suddenly stopped and it is a over compound generator. So if it's a over compound generator was operating properly and supplying power to the infinite bus. Okay. It's a over compound generator. If it's a over compound generator, the characteristics of over compound generator is somewhat like this, right? That is the characteristics of over compound generator with load current. Okay, and it is cumulative, of course. It is cumulative, of course, here. Okay, now what will it work as? Will it work as a differential or cumulative one? That is what I want to know. So prime mover has suddenly stopped. If prime mover has suddenly stopped, then the speed is 0. Then the generated EMF also will be 0. Okay, and so what will be the flux? So there will be huge current flowing, right? Huge current flowing. IA will be basically VT, the terminal voltage, divided by the armature resistance, because the machine has stopped rotating. There is no EB. So IA is this value. So now also the direction of current will be in the opposite direction. Previously, if it was operating as a generator, then it would have supplied the current, right? It would have supplied the current, case 1, but as it is now operating as a motor, it will receive the current, right? Case 2. So if I see the previously, remember the shunt flux direction does not change. So previously phi was equals to phi sh minus phi se plus phi se, right? Because it is over compound, so it will work as a cumulatively compound motor. So both the flux will be added. But now the interesting fact is, I see that the series current direction has direction reversed. Series current direction has reversed, but this has not reversed. So phi sh is still same. So ish direction same. So what will happen? So the flux phi dash will be now phi sh minus phi sh. Sorry, phi sh minus phi sh, because the direction has reversed here. The direction has reversed, right? Because the series previously the current was in this direction, now the current is in this direction. So current is opposite. So it will operate as a differentially compound motor. It will not operate as a cumulatively compound motor. So this is the property, right? So now what will be the direction of rotation? How can I understand the direction of rotation? Okay, so the direction of rotation that I want to discuss, so that will be defined by the torque and the armature current. So armature current itself has reversed its direction, correct? Armature current itself has reversed its direction. So armature current is now negative, so it has reversed, right? Current direction change, right? Armature current has reversed its direction. Okay, what about the flux? So what we assume, what we generally assume is that, like they should have here also mentioned that considering shunt to be dominating. Why? Because initially EB is 0. If EB is 0, okay, IA will be very high. Okay, how can I assume shunt to be dominating? That is not correct, right? But our assumption generally, that is the most cases, that shunt will be dominating. Okay, you will always assume that shunt will be dominating. So you can write again, whatever will be the increase in series flux, still this will be positive. If this is positive, overall the torque will be negative. So if you are following this, you are actually wrong. So I will suggest you, don't follow this approach for cumulatively or differential compound motor. Okay, don't do this. Machines, you draw the diagram. So what we know is that overall assumption is that overall flux, it will operate as DC differentially what do you call differential compound motor, but assumption is still the flux, the shunt flux will be dominating in nature. So if I draw the motor, and if initially in case of generator this was the north pole and south pole, and this is my armature, okay, and let's assume the armature rotor directions. Okay, very bad very bad drawing. So this will be basically, let me assume initially armature current was going into the screen and coming out from here, right? So how will I determine the direction here? So and initially, sorry, okay, how will I determine the current direction? That is what I want to know. So initially let's assume that in case of generator I was rotating in the clockwise direction. If I rotate in the clockwise direction, I will use the, for a generator I will use the Fleming's right hand rule. Remember first lecture, right? For a generator I will use the Fleming's right hand rule to determine the direction of the current. So if I see, the field direction will be here. Okay, so this is the forefinger is the field direction, the thumb is the direction of the rotation. So for this conductor it is going in the upward direction, so thumb will be upwards and the middle finger will be going inwards. So the current direction for generator will be inwards. Okay, and from here it will be outwards. Now what will happen for a motor? For a motor, basically I know the current direction. So whatever was the previous current direction, it will reverse, because IA has now become, IA dash is minus of IA, because we have what? Now the supply is delivering the power. So obviously the armature current direction is changed. So if the armature current direction is changed, that means what? That means now this will be dot and this will be cross, and the field direction flux is still positive. So phi dash is still greater than 0. It is still positive, just like the previous case. Okay, so field, this north pole and south pole will still be north pole and south pole only. Now I will use the Fleming's left hand rule, because for generator we use the Fleming's right hand rule. For motor we use the Fleming's left hand rule. Okay, so if I use the Fleming's left hand rule, what does it mean? So here, right, what is the direction of the current? Again, direction of the current will be given by the middle finger. So this time current is coming outwards towards me, and the field direction is like here. And if I see, the thumb direction is top, and for this conductor the thumb direction is top. So here the direction of rotation of the motor is top. Here it will be just the opposite, down. So again, in case of motor as well, it is clockwise. So direction of rotation will not change. Okay, so direction, hold on a second, no, it is correct. Yeah, direction of rotation will not change. Yeah, direction of rotation does not change. Okay, so here this will be the correct answer. Option D will be the correct answer for this question. Okay, let's now solve the next question. So in this question, what is the effect of reversing the supply terminals of a DC shunt motor? So if I reverse the, like, this analysis is easier. If I reverse the supply terminals of a DC shunt motor, what will happen? Basically, now this will be minus, this will be plus. So Is will be going here. This will be the direction of the Ia current. So Ia dash. So let me name it as Is dash. Let me name it as Ia dash, and let me name it as If dash. So if I see that the field current direction also has reverse, the armature current direction also has reverse. So this, in this case, we can easily analyze using the torque relation, that both phi dash is negative, phi dash and Ia dash has reversed. So basically what will happen? Torque direction will remain same. So torque will be positive only, torque direction will not change. So torque will be positive. So the motor will rotate in the same direction at its normal speed. Whatever was the speed, motor will rotate in the same direction, because both the flux and the armature current both has changed their direction. So values will not change. This phi value, Ia value will not change. Just the signs has changed, and negative into negative is positive. That's why this will be still B. Okay. Now one more question: why DC series motor is suitable to use as a universal motor while DC shunt motor is not? Okay. So in case of DC, like, what is universal motor? So universal motor is those kind of motors where both DC and AC supply works. Okay, both DC and AC supply works. So for a DC shunt motor, what is happening is, in case of a DC shunt motor, my torque is proportional to flux into armature current. Okay, and my speed is proportional to Vt minus IRA divided by flux. So my flux is proportional to the armature current. Now one more thing we know, that motor should operate both in AC and DC. And what kind of field windings? So I will discuss about that. I will come to this, why series winding is used. That actually there is a different topic where we will discuss after induction motors. We will discuss about this, don't worry. But for now, just understand this, that it has to operate very well in AC. So in case of a shunt motor, in case of shunt motor, okay, in case of shunt motor, what will happen? Just hold on, I will just check the volume. Yeah, volume is fine. In case of shunt motor, I know that the number of turns of shunt is very higher than the number of turns of series winding, right? Because the resistance is very high. To make the resistance very high, the basically area is smaller there. If area is smaller, resistance is made high, and yeah, because we discussed about this, right? If area is smaller, then the basically it has to produce the same amount of mmf. So even here in this case the field current will be lower, so as it has to produce the same amount of mmf, so my number of turns will be should be higher, because to make mmf higher. So now one more formula we know, that is the inductance formula. So inductance formula is equals to n square upon reluctance. If you remember this formula, right, it was n square upon reluctance, right? So what is property of inductance? Property of inductance is the opposition of change in current. So in case of a shunt winding, the shunt winding will have higher inductance than series winding. So shunt winding will have more opposition to change in current than series winding. So series winding will allow the change in current, right? Shunt winding will not allow the change in current. So that's why series winding is preferred than shunt winding. More about this we'll discuss in after the induction machine, or wherever we'll discuss, right? We'll discuss about this. Okay. Later we'll discuss about this. That what is a universal machine, the working, the diagrams, all those things we'll discuss. Okay. So that's why the series winding is suitable than shunt winding. Let's read this next question. The load versus speed torque characteristics of a particular industrial load is shown below. Which type of motor is most suitable for driving this load? So if I see, with increase in torque the speed is decreasing. It is like hyperbolic, right? It is hyperbolic. With increase in torque the speed is decreasing. If I remember that torque was proportional to 1 by under root of T in case of a DC series motor. So you have to sometimes remember this DC series motor. For a shunt motor, what was the case? For a shunt motor, if I remember that the flux was constant, right? So basically speed is proportional to Vt minus IARA divided by flux, and torque is proportional to flux Ia. So basically I can write speed is proportional to Vt minus T into Ra, right? So basically flux is constant. So basically it will linearly decrease, right? That is not suitable here. It is hyperbolic, so that is suitable for DC series motor. That's why option C will be the correct answer in this case. For an electric motor operating at constant output power, the torque speed characteristics will resemble constant output power. Okay, they're telling me electric motor is delivering a constant output power, so P is constant. Now what is P? What is the developed power at the output of the motor? It is omega into T. Omega into T, right? Omega M. This is the mechanical power into the torque of the load. Correct? So omega into TL is constant. So they are telling me what will be the torque speed characteristics. So from here I can directly say that torque will be inversely proportional to speed, or speed will be inversely proportional to torque. So it will be like a rectangular hyperbola. So option D will be correct. All these other options are incorrect. Okay. So that is what this will be. This we will discuss in the speed control in the next lecture. If a DC motor's armature is powered by a constant current source and its field winding is energized from a constant voltage source. Okay, DC motor power is energized by a constant current source. So the current IA is constant, they are telling me, and its field is energized by constant voltage source, so the flux is also constant. So I can directly say that the torque will be flux into armature current, that is torque is constant. Okay, now what they are asking, what would be the nature of its torque speed characteristics. So torque will be constant no matter whatever is the speed. It does not matter whatever is the speed, torque will be constant. So here, right, if I see torque is changing, so speed is constant. No, here I see torque changes, speed also changes. Here I see torque changes, speed also changes. No, here in this graph I see whatever is the value of speed, torque is constant. So I should have written the options A, B, C, D. So option B will be the correct answer in this question. Okay, let me do the next question. After that we are done. छुट्टी, आज के लिए छुट्टी आपको, ठीक है. I know it's like suffering listening to me for all these hours. I do understand. Okay, so a DC motor operates at 500 rpm at a supply voltage of 220 volts. To control its speed, 4.5 ohm of resistor is added in series. If the armature resistance is 0.5, what is the current required to bring the motor to stand still condition? How do I bring the motor to stand still condition, that is stall condition? That basically means that the speed will be 0, that is omega will be 0. How can I make the omega to be 0? Omega would be 0 if the back EMF EB is 0. That is how we will make the, that is how we will bring it to the standstill condition, right? So what is the current required? So basically IA will be equals to what? IA is VT minus EB back EMF divided by RA. This time a external resistance is also there, RA plus RXT, right? So if I want to bring it to standstill condition, it will be basically equals to VT, they have given me as 220 volts, minus EB is 0 because it is at standstill condition, RA is 0.5 plus 4.5, so this will be 44 amperes. So the armature current required will be 44 amperes to bring it to stop condition or stall condition. So this will be the answer. Okay, so these are like ESC, those kind of questions they can ask, but in GATE, like this was simple. I don't feel they will ask. Okay, so that's it basically for this lecture. Thank you for listening throughout the lecture. I will see you in the next lecture with the speed control of DC motors. Thank you and happy learning.